When it comes to artificial intelligence in games, choosing the best action to perform is crucial for survival or victory. The current situation needs to be observed, and the appearance of critical thinking needs to be shown. Having good artificial intelligence will bring life to a game and prove it to be challenging. Like any solution that should be solved, the objective of any powerful artificial intelligence algorithm is the same. We wish to implement an algorithm that can take whatever scenario we want and request what the best move is for us or the computer to take. Some people use a powerful artificial intelligence algorithm every day without realizing its potential in other games. Chess, a two-player strategy game played on a checkerboard, is a perfect example of critical thinking in a game. The objective of chess is to enter a state where the opponent's king is under immediate attack, known as check, and to prevent the opponent from moving to avoid the attack, which is known as checkmate. You typically strategize by thinking to yourself, if I move my rook to this position, the opponent can make this next move, and I can counter with this, with the following move, and it continues until you are satisfied with your move, or you decide to think of a different move. The simulation shown results in a checkmate, therefore we know which move to perform. The critical thinking of chess by performing the act of playing out the game in your mind is the center of the artificial intelligence concept that we will be discussing today, which is Monte Carlo Tree Search. This algorithm is very powerful and customizable. A tree configuration is used because the state will need to have nested states that are connected, and this can become deeply nested depending on the root state and the complexity of the game. The object of the algorithm is to take any current game state and provide the best action to choose. There are 4 phases to Monte Carlo Tree Search: tree traversal, expansion, rollout, and back propagation. For this algorithm, nodes are referred to as states. Tree traversal phase chooses a state in the tree that maximizes an upper confidence bound for trees, known as UCB or UCB1. Nodes with higher scores are chosen, but nodes that have been visited less are preferred. Node expansion phase adds additional states or nodes to the tree configuration. Rollout phase performs a random simulation of the game to find a value, typically until a terminating state is reached. Backpropagation phase takes the value from the rollout phase and puts it all the way up the tree to the top, using the parents of the nested states. Alright, so let's take a little bit and discuss the UCB1 formula. So this is typically UCB or UCB1, upper confidence bound for trees. It's for any given node. You calculate the average value of the node by taking the current score of the node divided by the amount of visits that node has been visited. And then you add to a second part of the algorithm, which is taking the natural log of the parent node's visit count divided by the visits of the node. And that's all square rooted and multiplied by some constant. Now the constant here is what we use to balance the exploitation term and the exploration term. So that natural log divided by the visit node, all square rooted, times some constant, plus the average value of the node. That is the formula for the UCB1 value that needs to be used during tree traversal phase. Let's take a look at the rollout phase next, and what a rollout does is it loops through, it does a random simulation of the game. It actually performs the game based on the current state. So the pseudocode, the general algorithm of this phase is to loop forever. If the state is a terminating state, it returns the value of that state. Otherwise, it picks a random action available from the current state in the simulation, and then it updates the state in the simulation to actually perform that random action. So it's basically the example of chess earlier in the video where if I move my rook here, then the player can move their king here, and then I can move here. So you're actually playing out the game during this rollout phase. You typically result in a value from a terminal state, or some limitation is reached. For example, you have reached the time limit. All right, let's take a look at the breakdown of the algorithm in general here. So we start the algorithm by accepting any given state of the game. We set the current state is equal to the root state. Now the root state is the initial state, so we're going to do some setup up front. For each available action from the current state, we'll add new states to the tree, and then we'll set the current state to the first new child node. Then the question is asked, is the current state a leaf node? If it's yes, we check, is the visit count for current 0? If that node has not been visited before, we perform that rollout phase. We get a value, we backpropagate all the way up the tree, then we repeat the tree traversal process. We pick a node that maximizes the UCB1 score and choose that node. Is the current node a leaf node? Yes. Is the visit count for current 0? No, we've just visited it, so we need to perform the expansion part of the algorithm, which is for each available action of current, we add new states to the tree. Current is equal to the first new child node, and then we perform a rollout from there. Backpropagation is performed, and tree traversal is performed again. We check, is current a leaf node, and this time it is not a leaf node. So we perform tree traversal again, and we go down the hierarchy, down the levels of the tree. So we perform tree traversal again, and check, is current a leaf node? Yes. Is the visit count of current 0? Yes, and we perform rollout. So this entire process completes until something occurs, which we'll discuss now. Monte Carlo Tree Search is based on limitations. As we just discussed, the algorithm can loop constantly, loop forever. So we need to provide some limitations on the tree. We could let the algorithm run for several hours on any given scenario, but this is not valid for a video game where decisions need to be made quickly. Typical limiters include time and depth. The average human reaction time is 250 milliseconds. This can be used in a fast-paced games as a limiter for quick actions. Depth is reasonable for limiting how deep a tree gets before a decision is made. Multiple limiters can be in place to make the algorithm fit the needs of your desired situation. For example, a chess scenario could only have the time limiter, which is set to minutes instead of milliseconds. In general, the longer the algorithm can run, the better the results will be. We're going to take a look at a very simple example in order to understand the algorithm a little bit more. The limitations we will be using will be a variation of the depth limiter, to limit the number of visits that have been performed globally on the tree to 5. The algorithm takes an initial state, S0, and immediately adds children from the available actions. The first child node is chosen, S1, and a rollout begins. Random actions are performed until a terminal state is reached. A value of 5 is generated as a result, which needs to be backpropagated up the tree, updating scores and visit counts along the way. Tree traversal is performed, but a UCB check is not required if a node exists in the current level of the tree that has not been visited before. The reason for this is because a division by 0 will occur. Therefore, we choose the first non-visited node at the current level, typically by order. So this would be S2 in this case. The algorithm checks if the node is a leaf node. S2 is a leaf node, so the next question in the algorithm is if the node has been visited before. This node has not been visited before. It has a visit count of 0, so a rollout is performed. A series of random actions is performed and results in a value of 3. Backpropagation is performed up the tree. Tree traversal is performed. UCB1 check needs to be performed for this iteration since both S1 and S2 have visit counts greater than 0. S1 has a score of 5 and a visit count of 1. So the average will be 5 divided by 1. The constant we provided to the algorithm is 2. S1's parent node has a visit count of 2, and S1 has a visit count of 1. So the natural log of 2 divided by 1, all square rooted. This results in a UCB score of 6.6651 for S1 state. S2 has a score of 3 and a visit count of 1. So the average will be 3 divided by 1. S2's parent node has a visit count of 2, and S2 has a visit count of 1. So the natural log of 2 divided by 1, all square rooted. UCB1 score of S2 is 4.6651. The algorithm chooses the node that maximizes the UCB1 score, so S1 is chosen. In general, the algorithm chooses the node with the higher score, but favors nodes that have been visited less. S1 is a leaf node, and S1 has a visit count of 1. The expansion process is performed for S1, resulting in new states S3 and S4. The first child node is chosen, S3, for a rollout. Rollout value results in 7, and backpropagation is performed, all the way up the tree. Tree traversal is performed, resulting in S1 and S2 getting UCB values of 7.4823 and 5.0962 respectively. S1 is the node that maximizes the UCB score, so it is chosen. S1 is not a leaf node, so tree traversal continues. At the current level of the tree, there exists a node that has not been visited before. UCB scores are not needed to be checked. The first node in the list that has a visit count of 0 is chosen, S4. A rollout is performed, resulting in 1, which is backpropagated. Tree traversal occurs and UCB check is performed for nodes S1 and S2, which result in 5.6928 and 5.3548 respectively. S1 is chosen. S1 is not a leaf node, so tree traversal occurs again. UCB scores are checked for nodes S3 and S4, which results in 9.0962 and 3.0962, respectively. S3 is chosen. S3 is a leaf node. S3 has been visited before. Expansion occurs, resulting in new states S5 and S6. S5 is chosen as the first child node, and rollout is performed. A value of 0 is produced, which is backpropagated. The algorithm has hit the limit of number of visits it can perform that we specified, which is 5. The best action is chosen by which direct child node has the highest score. A1 is selected as the best action. This is a very powerful algorithm, but as you can see, it's not that complicated. It's the act of playing out the game and determining some value for your actions. This example was very basic. It didn't have any kind of information regarding the state of the game. It was just some state S1, some state S2. In another video, the next video, we will actually take a look at a real-life example. This is just to introduce the algorithm and show you the process of performing it before we throw in an actual game state, which will be 2 things to worry about instead of 1 thing for this video and 1 thing for the next video. There is some things to consider with implementing this algorithm. Depending on the complexity of the situation you want to solve and how many available actions that branch out from these scenarios, it can be quite memory intensive and quite time intensive, which if we're talking about a video game, we want things to perform as quickly as possible, unless you're working on a game where you can give it some 30 seconds or a minute to think. In most games, you pretty much want a response right away. I believe there are a few games that the computer's action can take about a minute, and you kind of have to balance that out with your game design and your player base's patient level, their ability to wait for something to happen. So it's best to, if you have a very complex game, it's best to limit the state that we use to check to a state dedicated to Monte Carlo Tree Search. You don't have the entire game state in the test. You kind of create a Monte Carlo Tree Search state based on your current state. Only provide the necessary details. For example, your player's health and your enemy's health. That's the only 2 things you provide to the state for this algorithm, instead of having all this other information, all the NPCs and all the text and all the other attributes that none of these other players the algorithm cares about. So just feeding the state into the algorithm is not a good idea. It's best to transform it to a very minimalistic object so the algorithm can work on it as memory efficient and as CPU efficient as possible. As you saw earlier in the video, the tree can branch quite large, and I stopped it several levels in So you can imagine if we let it go for about an hour, each one of those states is its own copy. Because we need to reference that. We need to reference what the player's health or what the action was to get to that state. We need to reference all the way down. So having a copy of all these big states can be taxing on your RAM. So I just wanted to narrow that down in this video. We will discuss a real-life example in the next video, and it will be a very basic state. The game that it's coming from is quite large, but I provided just a few details that the algorithm needs. It doesn't need anything else other than what it has. Well, that's it for this video. This has been a long time coming. It's actually a algorithm I implemented in my game project, and that's what the next series of videos are going to be based on, is the concepts and ideas I have that my game project is using currently to make the game pretty well designed and a pretty good, decent game. So stay tuned for those tutorials. So next video, we're going to continue with the Monte Carlo Tree Search discussion, and we're going to take a look at a real-life example coming from a snippet of my game. I didn't include a lot of complicated actions or states. I just took a snippet so I can quickly and more efficiently discuss in a video fashion for you guys. But it's a real-life example. We have a game state, and we want to know what the computer's actions should be based on the state. And we'll perform the same thing we did in this video, where we will actually perform the tree traversal, expansion, rollout, and backpropagation. We'll do that until we reach our limiters, and we will determine the best action to go with. So, thank you for watching. I hope you learned something useful to incorporate in your projects. Stay tuned for the next video, and I hope you have a nice day.